So this talk is about radio astronomy, and many of you may not. Some of you were in Astro 214, have a little background. Some of you are just interested in astronomy, so you may not know what radio astronomy is. So like all of astronomy, radio astronomy is the study of the sky. We look at planets, we look at stars, we look at galaxies, other things that are out there. And like what you think of with telescopes, we point telescopes to gather the signals from the sky. And like with optical telescopes, we sometimes make pictures, but not always. I mean, if you're looking at a star that's variable, it just looks like a dot in the sky. But it gets brighter and fainter, and that can be important. So we don't always look at images, but of course, plots of things going up and down are not very exciting to show the public. So I'll try and show you images as much as possible. The difference for us is that instead of using light, instead of using the light you see with your eyes, we use radio waves to look at the sky. So radio waves, just to clarify the difference, well, light itself is a wave. It propagates through space. It's different colors, different pure colors are different wavelengths. So red might be 700 nanometers, blue might be 400 nanometers. This is about 500, this green. Mixed colors can be a combination of several different wavelengths. But wavelength determines sort of the color of the light. And if light is shorter than 400 nanometers, it's ultraviolet. And it can burn you, but you can't see it. If it's even shorter, it can be X-rays or gamma rays. And again, it can affect you, but you can't see it with your eyes. Longer wavelength light is infrared is longer wavelength, for example. And even longer wavelengths are radio. It's the same sort of wave, same propagation through space, but the wavelengths are much longer. A nanometer is 700 nanometers is a little more than half a micron, half a millionth of a meter. For radio, we use a few millimeters to actually tens of meters, to waves long enough, the wavelength is the size of the room. Can people in the back hear me okay? I don't have a microphone, unfortunately. Cool. All right, so just an illustration from NASA of wavelength, that visible light is this little narrow range of wavelengths, but as you go to shorter wavelengths, you get quite different radiation, and longer wavelengths, you get quite different radiation. And when I say radiation, light is radiation too. This is not the stuff that you worry about coming out of the Fukushima reactor. Well, this stuff is, but radio waves are basically harmless, unless you stick your hand in a microwave oven. So just to be specific, what I mean by radio waves. The wavelengths are from more than 100 meters length down to about 1 millimeter. These pass through the upper atmosphere. The atmosphere doesn't block these as long as they're shorter than about 10 meters. Beyond 10 meters, they actually bounce off the upper atmosphere, which is great if you want to talk to Australia with your ham radio, but which is not so good if you want to see the stars, because the waves bounce right off. The way you detect these things, you don't use your eye, obviously. If you'd like a seat, there are a couple over there. If you obviously don't detect these with your eyes, because, well, your eyes can't sense them. We use antennas and we use electronics. And for those, the technically minded, the criterion I'm using for what I consider radio is that we use heterodyne detection. It's a particular way of detecting it. We actually just measure voltages as opposed to heating a little element or lighting up a CCD or something. So it's a particular way of detection. And we use radio waves for communication. If we're going to look at the sky, you have to ask, what is it out there that makes radio waves? Well, unfortunately, people make radio waves. Your cell phone communicates with radio waves to the cell phone tower. Wavelength is a centimeter or two. FM radio is radio waves. They're like 3 meters wavelength. Microwave ovens, again, a centimeter or two. Radar antennas send out radio waves. Sparks produce radio waves. So there's a lot of stuff on Earth that produces radio waves, which is kind of a pain for us, because we want to hear the stars, and somebody's cell phone next to the telescope is much brighter than the stars that are light years away. But there are things out there that produce radio. Planets produce a little bit of radio. And like sparks produce radio, so lightning produces radio, so the Earth makes its own radio waves. Some of the other planets, Jupiter produces radio waves, and I'll show a little bit of that later. Stars produce a little radio waves, but not much, not compared to the light they pour out. But what really produces a lot of radio waves is first of all, hot, thin gas. Like a neon tube produces light of a particular color when you run electricity through it. And of course, that color is visible. It's visible light. It's very short wavelength. But there are other gases that, if you do other things to them, produce much longer wavelengths. Hydrogen, for example, produces 21 centimeter wavelength radiation. And so this hot, thin gas in the universe we can see, and it has special wavelengths, and we can do some clever things with that. But mostly what we see is plasma. Now, you may not have heard talk of plasma in your science classes, but it's what you get if you take matter and you heat it up so much that the atoms get ripped apart. The electrons get pulled right off the atoms. And those loose electrons, those loose ions, that's great for producing radio waves. And we're lucky, planets and stars don't show up much, but luckily most of the universe is made of either hot, thin gas or plasma. So there's lots of stuff we can look at. And from my point of view, it's the interesting stuff. It's, you know, the star, there are stars, there are planets, but they're kind of boring. But there's huge explosions, there's jets of material being blasted into interstellar space. That stuff shows up great in radio. Now, to look at this stuff, we need telescopes. And an optical telescope, this is actually the one on the roof that you'll be using later if you stick around. You need several parts. You need a support to point it in the right direction to track things across the sky. You need some mirrors. You know, the light comes in the front, bounces off the back, bounces off the front, comes out. So you need some mirrors to focus the light. And you need a detector. In this case, you just put your eye out. A radio telescope needs the same things. You need support to point the telescope. You need a reflector to focus the radio waves. And you need a detector to sense the radio waves. But things are a little different for a radio telescope because the radio waves are much longer. That was our criterion. And things get quite different when we get longer waves. So some of the things that change are good. You know, if you take a piece of metal and it looks all dirty and scratched up, and you start polishing it, it looks scratched, and you polish it, and polish it, it gets smoother and smoother, and then it looks shiny. And the point where it starts looking shiny is where the kind of scratches get smaller than about a 20th of a wavelength, and then like at 10 nanometers. That's when it gets shiny. That's when it makes a good mirror. And if you want it to be a perfect mirror for a telescope, you need it to be accurate within about a 20th of a wavelength, so a few nanometers. And a few nanometers, it's really hard to make something that stays a few nanometers accurate when you tip it around and you point it all over the sky. So it's hard to make a big mirror for a telescope. We do, but it's hard. If your wavelength is 20 centimeters, then if you've got bumps that are a centimeter wide, it's not a problem. You can use chicken wire. Literally, you can use chicken wire. So it's much easier to build a great big telescope, which is a good thing because the size of what you can see on the sky is proportional to the size of your telescope divided by the size of your wavelength. And so Hubble has a 2-meter telescope and a 500 nanometer wavelength. To get the equivalent of that to 20 centimeter wavelength, you would need a 40-kilometer telescope, which is not easy. So we have to either build gigantic dishes or we have to cheat. I'm going to give you some examples of telescopes and explain what I mean by cheating as well. The first telescope I'm going to talk about, this is the Green Bank telescope. Now you can't really see how big it is here, except this fence is, about as high as you can reach. This is a big telescope. There's an elevator up there, and that little tiny box is a cabin you can go into and work on the receivers. So this is a big instrument. So it's officially the Robert C. Byrd Telescope at Green Bank, named after Senator Robert C. Byrd, who recently passed away, who was a senator who's specialized in getting government projects built in his economically depressed state. And this is situated in the town of Green Bank, West Virginia, population 143. Now, there's a reason for that, and there's a reason it's in a little farmer's field with some mountains behind it. Because remember all those cell phones that are producing radio? This thing is very sensitive to cell phones, and we don't want to hear them. So you put it in a place that's so poor they didn't have any cell phone service or any radio stations, and doesn't have any radio amateur operators. And in fact, it's the National Radio Quiet Zone. There are laws about what you can build there, what you can do there. And they have a converted ice cream van with antennas on top. They drive around. And so farmers will get a knock on their door and be asked to repair their damaged electric fence that's making sparks, or replace their beat-up electric blanket that's making sparks. just to keep this quiet, to keep all the human-made junk out of the way. And this, too, is why we put it in a valley instead of on top of a mountain. Because on top of a mountain, you can look out and see all those cell phones, all the people around town. In a valley, the mountains keep some of that out. We still have problems. Every car produces sparks. Actually, right around the telescope, we only allow diesel vehicles because they don't need spark plugs. So we do what we can to keep terrestrial noise out of this thing. But it's still a problem. We struggle with it. But this telescope, it's 100 meters in diameter. And it's the largest in the world. Now, you have to be careful because there are bigger telescopes that you can't just point anywhere you like. And there's another telescope that's 100 meters in diameter. But this one is actually elliptical. It's 100 meters by 110, so it's the biggest. The Germans were a little bit unhappy when that came out. But this is quite a sophisticated telescope. It's made of little panels about 1 meter by 2. And at the four corners of each panel are these little actuators, so you can move. So that if the surface sags a little bit, it can kind of push the surface up into the right shape. If the surface is heated on one side by the sun, it can bend itself back into the right shape. This is a very sophisticated telescope, and that allows it to go down to a wavelength of 3 millimeters. That means it can keep its surface accurate within about 1/10 of a millimeter over that 100-meter surface. I mean, that's big enough. That length is enough that you could play a game of football on it. There's a great, I don't know if you've seen the movie The Dish, which is about a radio telescope in Australia, and it opens with the astronomers on a slow day playing cricket in the dish. And of course, you bat the ball, and it comes right back to you once it's worn itself out. So these are big instruments. But even with this gigantic dish, at 1 meter, the beam is still almost a degree on the sky. I mean, that's a little bit hard to visualize, but if you went all the way around the horizon, that would be 360 pixels around the entire sky. That's really kind of limiting. We have megapixel cameras. We can do much better than that in optical, even with a small camera. Even down at 3 millimeters, you do a little bit better. It's 8 arc seconds at those really high frequencies. But even that is still 10 times worse than the Hubble Space Telescope with a 100-meter dish. So how can we do better than this? Well, you can try and build a bigger dish. This is the predecessor to the telescope, 300-foot telescope at more or less the same site. And 300 feet is about 100 meters. But this was a previous telescope, and you can see it's actually quite thin mesh. But even so, it's 100 meters is about as big as you can build a steel telescope. As you make it bigger, you have to put more mass up there to support it. But then there's more mass to support, so you have to put more mass to support that. You start getting into an area of diminishing returns. And this one, turns out they didn't put quite enough mass to support it, because one morning, it looked like this. You can still find pieces of the wreckage in the fields if you go there. But this failed, and then they got government funding to build a nice big new one, which is great. So I can't be too unhappy about this, because the new one is wonderful. But so we can't build a dish much bigger than 100 meters. So what do we do? How do we build a bigger one? Yeah?
When did it fail?
This failed, I think, in 1993 or so. I don't remember the exact date, sorry.
How long after it was set up?
No, it ran for quite a few years. But ultimately it failed. There was one of the gusset plates just, I think metal fatigue just failed. So the next step is to build an even bigger dish, but don't rely on the dish to point just anywhere in the sky. And so this was built. This was actually older than the Green Mag telescope, but this is the Arecibo Telescope. You may recognize it. It appeared in a number of movies. They digitally erased the reflector because it was less interesting.
I'm ready to see about the satellite.
How are you stopping?
The transmitter above the entire.
I don't know if you can see. This is real stuntmen doing this. Just how big that dish is. But it's hard, this thing is so big it's hard to picture. It's 300 meters in diameter. It's actually convenient because the runners who go to the club, the runners who go to the observatory like to do a lap around it every morning. It's a nice even kilometer lap. It's, you know, so this is near Arecibo in Puerto Rico. And the way they built it is they put it in, the geology there is this limestone karst, which is ridden through with limestone caves. And so if you go there, just go caving. It's awesome. But those limestone caves get bigger and bigger as the water runs through, and then they collapse. And so you get a certain number of fairly circular valleys. And so what they did was they took a circular valley. The story goes that they took the contour map at a dime and slid it around until they found the contour that lined up nicely with the dime. So they took a nice circular valley, and they basically slung a mesh dish over it. So it's slung on an array of cables. It's a bit like a stadium roofing construction, except it curves the other way. And then, you know, you have cables running down to concrete posts and turnbuckles. You can adjust it if it gets out of shape. And again, it's just kind of mesh. And actually, underneath there, you can go under there. There's a tractor there. They do maintenance underneath. And in fact, that hole in the center is so they can hoist stuff up and down directly to the central platform. You can go under there, and it's a weird experience because it's like walking through the jungle, except it's curving the wrong way. The roof curves the other way from how you expect. And it's a unique ecosystem because it's kind of partly screened from sunlight, like the jungle floor, and the rain sort of drips through, but nothing can grow tall or they cut it down. So it's kind of a strange ecosystem that's grown up under there in the 30 or 40 years since it was built. But the way that you observe with it is there's this suspended platform, and this arm rotates. You can see the round track that it runs on. So this rotates around. And this Gregorian dome moves back and forth along that arm. The long spike is mostly obsolete now, even though it looks cooler, so they kept it in the James Bond movie. But as a result, by moving this around, you can look not just directly overhead, which is the easiest, but you can look about 20 degrees away from vertical, which gives you a patch of sky you can look at. It's not the whole sky, but it's a patch of sky. And it's a small price to pay for having a telescope with 3 times the diameter. And this little video, I'm afraid it's a little hard to see, but this is the Gregorian dome. You can see it moving around. And so the arm rotates and the dome moves in and out to pick a point on the sky. Now this is a time-lapse video because it takes about 15 minutes to go all the way around. Just because this arm is actually 100 meters long. This arm is the size of the entire telescope before. This is a big instrument. You know, so it has receivers that cover about 1 to 3 centimeters. It doesn't go as small as the Green Bank telescope because it doesn't have as good a surface. And it has this, I guess, innovation, for lack of a better word. On the Green Bank telescope that I showed you, they have a set of receivers, but only one can be active at once. You only have 1 pixel, essentially. You only get to look at 1 point on the sky at a time. If you want an image, you have to kind of laboriously scan back and forth. And the reason for this is that you don't just have a CCD with lots of pixels. You have a full radio receiver, cryogenically cooled, that we use essentially liquid helium to cool our receivers. So it's not easy to build many receivers. But at Arecibo, there's this alpha receiver, which has 7 beams. We've upgraded from 1 pixel to 7. And this is a big upgrade, but it's still nothing like the optical. The optical people have got megapixels, right? We have 7 pixels. And even with 300 meters, you've tripled your resolution, but it's still nothing like the resolution you have in optical. So it's great, you can collect lots of signal, you can measure things, but it's hard to make nice images. So we need a bigger telescope, but valleys bigger than 300 meters are hard to find. It's hard to build giant suspended dishes that big. So what do? We cheat. This is where the cheating starts. This is the Very Large Array, which, again, you may recognize from the film Contact, although they had to digitally enhance it to the film. And we don't actually use headphones when we work. But the Very Large Array is it's in the plains of San Agustin, New Mexico. So it's a big space of big empty, just like the Green Bank telescope. It's 27 different telescopes, well, 27 identical telescopes on railroad tracks. So you can put them in an arrangement. And they actually have these little railroad carriers you can load them onto and wheel them around, which they do 3 times a year. And The reason they do this, the reason they build them around, the reason they have 27 telescopes is that all track together, is that you can coordinate them using a trick called interferometry. And when you do this, your 27 antennas act like one giant antenna. And it's not just an antenna that has 27 times the area of a single antenna. That's how much light it collects. But if you coordinate them correctly, you can get them to act like a single antenna the size of the separation. So when you spread them out over 36 kilometers, you have effectively an antenna that's 36 kilometers across. And remember I said that to duplicate what Hubble does with 20 centimeters, you would need a 40-kilometer wide antenna? Well, we have one. You can wheel these things out to 40 kilometers apart, you coordinate their signals just right, and you get the same kind of angular resolution as Hubble does. Now, I have to say this image is a little bit of a cheat. I feel compelled to mention it. This is actually the dishes themselves. But the blue part is an optical image of the sky. And the red part is an image of a galaxy they produced. An image of some jets streaming out of the galaxy M87. And one of the advantages of this is that because the way you coordinate the antennas is clever digital magic, which I don't want to go into because it's sophisticated. Using this clever digital magic, these 37 antennas, you can produce a whole image, this whole image from a single point. You point it once, and you can sort of synthesize many, many pixels from that one image. There are problems, there are headaches, there's a reason they shrink it down to smaller sizes for various observations, but altogether it's an extremely powerful technique for getting high-resolution images, even with this very long wavelength that we're observing with. So interferometry is a powerful tool, and the VLA is a great instrument. But it gives you the resolution of Hubble. What if you could build a bigger antenna? I mean, after all, it's the separation of the antenna that gives you the resolution. So what if we could put the antennas further apart? The very long baseline array does exactly that. The antennas are actually a lot like the VLA antennas. They're the same 25-meter dishes. And there are only 10 of them. But one of them's in the US Virgin Islands, another one's in Hawaii, and the rest are all over the continental US. And together, this can produce images. The way you coordinate the antennas is you point the data, point to the sky, you record the data to hard disk packs in each one, multi-terabyte hard disk packs. You ship them all back to Socorro, a giant computer chugs away at them for a few days. And at the end of it, you get images. And if you did everything right, you have a telescope the size of the Earth. And with a telescope the size of the Earth, you can actually produce the highest resolution images in all of astronomy. More so than optical, more so than any other band, you can get really high resolution images of the sky. Now, there are limitations. Your images tend to look kind of blobby, but you can observe. You can look at little tiny things, or great big things that are really, really far away. So that's for the telescopes. And there are, of course, lots more telescopes than this. There are new telescopes going up all the time. But I think we should start talking about what's out there in the sky. So generally speaking, what do we look at? Well, we can look at the solar system. There's the planets, the asteroids are interesting, the sun is interesting. You can look at our galaxy, either things that are in our galaxy, stars, or things that come from stars, like nebulae, sort of hot clouds of gas from various sources. You talk about gas clouds, clouds of cold hydrogen gas. You can look at the structure of the Milky Way itself. You can look at other galaxies. I mean, there are other galaxies out there, and with the Hubble, you see kind of swirls and blobs. It's kind of interesting. But optical people are crouching at me just saying this, but there's not that much to see optically. But with radio, you can really start probing what's going on in them. You can measure the motion of the stars in these other galaxies. Many of these galaxies have black holes in them. You can look at those black holes. So you can do a lot of work on this. And then, of course, if you want to look further away, you can look at the Big Bang itself. The cosmic microwave people here are going to throw things at me if I go into that too much. So some particular things to look at. You can look at Venus. Now, this, I don't know if you know much about Venus. It's in some ways our nearest neighbor, but it's blanketed by clouds of opaque sulfuric acid at all times. No breaks in the clouds on Venus. The Russians landed a couple of satellites on it, but they lasted just a couple of minutes before they melted. The temperature is hot enough to melt lead, and the atmosphere is pure sulfuric acid. So it's hard to build something that will drive around and explore. But with radio astronomy, you can actually map Venus. They have. This map is, I don't know if you can see it, quite detailed, was produced using radar. So Arecibo, that great big dish, actually has a transmitter, has a radar transmitter. It transmits about 1 megawatt of radar. And so it sent out a beam of radar towards Venus. The beam came back and was detected with greenback. And by sort of carefully measuring the frequency and the time delay of what came back, they were able to reconstruct a detailed map of the entire surface, even though the clouds just don't show up on radar, on this kind of radar that we use. So you can see right through the clouds to the surface of Venus. And that trick, seeing right through the clouds, is something we're going to see throughout the presentation. It's one of the advantages of radio. Some of the things that block optical astronomy aren't a problem for radio. Asteroids are also interesting. I mean, they're kind of lumps of rock. They have interesting shapes. The generic term for them apparently is spuds, if you work in the business. Because they're kind of potato-y, kind of lumpy, roundish. This one, in particular, is 4179 Tuctatus. Now, I don't know if you read the Asterix comics as a kid, like I did. But the chief of the village was forever swearing by Tuctatus because he was afraid of the sky falling on his head. And this asteroid is actually named in honor of him. Because this asteroid has a few kilometers in diameter, which is not that big for a planet, but big for a rock. Big for a rock that might fall on your head. Because this one has a chaotic orbit. You can't really predict it that far ahead. It kind of orbits, it's affected by so many other planets, you can't really predict its orbit very effectively. And that orbit actually crosses the Earth's. Now, never at the same time as the Earth is there, thankfully. But it could be there at the same time as the Earth. The chances are pretty remote, but it could happen. And so it would be really nice to know if it was going to happen. I don't know if we could do anything about it. There were movies about this, but I don't know that we could really do it. But it would be nice to know, at least. And so radar lets you, I mean, you bounce a signal off it, you measure how long it takes to come back. You measure very exactly how far away the thing is. So radar lets us monitor the orbit of this asteroid and other asteroids that we don't know about that might cross the Earth's orbit and that we might want to know about before they hit us. So you can study asteroids with radio telescopes. You can study Jupiter. Now I realize this doesn't look like the Jupiter that you've probably seen pictures of, or that you might even see. Tonight Jupiter rises a little too late. It rises about 11 o'clock. I don't think we'll be able to see it through the telescopes here. But this doesn't look much like it with its red spot, because this is an image taken with a very large array. And Jupiter has a lot of electrical storms that show up pretty well. And you might ask, why isn't it round? Isn't Jupiter round? Well, actually, a lot of what you're seeing is Jupiter's rings. Now, Saturn famously has rings. Galileo said they look like ears or handles. Pretty fuzzy telescope. Saturn's rings are another thing that, unfortunately, rises in the mornings. We're not going to see them tonight, but you can see them with quite a modest telescope. Jupiter's rings you really can't see very easily with an optical telescope. They're pretty faint. They show up pretty well in radio. So you can see Jupiter's rings on this image. But the reason I picked Jupiter for this is that Jupiter is one of the most radio astronomy you need a giant telescope to do, unfortunately. We've got a little tiny one on the roof, but it can't do very much. But Jupiter you can actually hear on Earth. If you've got an amateur radio receiver and you've got a directional antenna and you point it in the right direction, listen about 20 megahertz. That's about 15-meter wavelength, which is doable at night. You can actually hear Jupiter. You hear storms on Jupiter. And I have actually recordings. I hope they come out okay. This is a recording of L bursts from Jupiter. Now, I'll admit it doesn't sound like very much. It just whooshes. But this is another planet we're hearing. This is lightning storms on another planet that we're hearing. In fact, Jupiter's satellite, Io, is volcanic. And there's actually an electric current flowing between Jupiter and its satellite, which is just plain weird. I'm sorry, there's probably a better way to say that in sciencese, but it's just plain weird. And you can hear it with a radio you can have at home. So I thought that was worth seeing, and it doesn't always do the same thing. These are called S-bursts. Now I'd like to have some fancy explanation that L burst stands for long bursts, and S stands for short bursts. So. But I'm going to move outside the solar system now, and I first have to give sort of something in the nature of an apology. The names for astronomical objects. There's a few familiar ones, like Jupiter, the Sun, Sirius is the brightest star, it's the dog star, because Sirius has something to do with dogs, I don't know. Fum al-Hut, it's the mouth of the whale in Arabic. The Guitar Nebula is named because it kind of looks like a guitar. A few objects have names that you can cope with. But there are a lot of things out there. And you don't want to have a naming argument about every single thing. So more of the objects, you know, stuff named in the 19th century tended to be named based on, I think Charles, was it, Messier, put together a catalog of things that weren't stars that were out there. And so Messier 87, you might see tonight, if you're lucky, is the Ring Nebula. And it looks like a ring. It's a ball of gas that looks like a ring. 368 is from the 58th object from the 3rd Cambridge catalog of radio things. Kesteven 75 is the 75th object from the Kesteven catalog of supernova remnants. Sagittarius A star is the part of the brightest thing in Sagittarius in radio. So a lot of things have kind of not very helpful names based on catalog numbers. But that's not very tenable either because, I mean, you have a different kind of name for things that might be the same kind of thing, but because somebody different notices it gets a different name. So these days, objects tend to be named based on their coordinates in the sky, which is even worse. So you might have a pulsar that's named PSR J1023 plus 038, because that's where it is in the sky. Or for you, 1820 minus 30, because that's where it is in the sky. Or G29.7 minus 0.3, because that's where it is. These are galactic coordinates, and these are right ascension information. Right? All this to say, I'm sorry, a lot of these names are going to look like gibberish, because that's the names of these things, because we ran out of comfortable names a long time ago. So, this object is about the brightest in the radio sky, so I thought it'd be a good place to start. This is Cassiopeia A. It's the brightest radio thing in Cassiopeia. It's actually what happened was a massive star, many times the mass of the sun, ran out of hydrogen, ran out of helium, started burning carbon and all the other heavy elements all at once and exploded. And I really mean exploded. It blew up. I don't know whether Cass A was noticed by people. Usually, a lot of these, they're so bright in the sky that people see them and record them. But Cassiopeia A exploded about 300 years ago, and so you have this shell of debris, basically, of hot plasma being blown outward at very high speeds. And of course, it's glowing under its own temperature, and of course, it's crashing into the tenuous stuff between stars. And so you see here, there's kind of a spherical, roughly, cloud of glowing matter. And it looks all kind of curdled because the medium isn't smooth and you get kind of irregularities developing, like when you turn a glass upside down, it doesn't all pour it at once, it kind of starts falling down one part before the other. That same process is making this kind of clumpy. But this clumpiness is illustrated, this here is a composite of 3 different images taken with a very large array at 3 different wavelengths. 20 centimeters, I think 5 centimeters, and 3 centimeters. So those 3 wavelengths measure different temperatures of the gas. Different colors here tell you something of the temperature, but mostly they're just 3 colors to make it look a little prettier. Because unfortunately, a lot of radio images don't look very pretty. They're informative, but they're not always pretty. So this next one is another supernova remnant, Kesteven 75, and it looks a lot more boring, because we only have one frequency. But you can still see it exploded from about here, and there's kind of a shell where the exploding material is crashing into the interstellar medium. This one was 700 years old, and it's a little different, actually, because this blob in the middle is, you can't really tell from here, but we've looked at it more closely, and you can tell that it's actually something a little bit different. It's not remnants of the original explosion. There's something else that's actually currently blowing out gas there. It's spewing out this, in fact, It's this mix of matter and antimatter that's being spewed out at high speeds, and it's crashing into actually the last of the debris from the original explosion. So we have this kind of ball of this nebula, this blobby piece of hot gas, the center. And the thing that's blowing out that material is what's called a pulsar. And I'm going to go on a little digression about pulsars because we study pulsars here at McGill, and I study pulsars, and so they're a favorite. I apologize if any of you were here for the pulsar talk that Ryan gave last year, because some of this you'll have heard already. But I'm going to focus on the radio side. And pulsars are in my opinion, one of the coolest things you can look out for the telescope. So, discovering pulsars in 1967, Anthony Hewish and Jocelyn Bell were trying to study quasars, far distant. It turns out they're called active galactic nuclei. We're going to talk about them later. But they were too small to see with the radio telescopes they could build. And this wasn't a dish, this was a big array of wires. Jocelyn Bell apparently spent all summer sledgehammering stakes to put that together. So they couldn't resolve this. They had the same resolution problem. So their trick was, if you go out and you look at the stars, they twinkle. You look at the planets, though, and they don't twinkle. And the difference is the planets are just big enough, not big enough that you can see a disk with the naked eye. They're just big enough that the twinkling doesn't cancel out the way that it does with stars. It's diffraction magic. But the point is that planets don't twinkle because they're bigger. So you can measure how big something is by looking at its twinkling. Now, they weren't looking at atmospheric twinkling. They were looking at twinkling due to the gas that's between planets. Nevertheless, they were looking for twinkling. And that meant they had to look at things that might change quickly, as opposed to averaging over minutes, like everybody else had done so far in radio astronomy. When they started looking for things that changed quickly, they found some. Now, most of it was, I guess, not cell phones in 1967, but radio or car ignitions or whatever, hair dryers. So Jocelyn Bell they were using chart recorders. Jocelyn Bell had literally miles of chart recorder paper sitting in her office that she spent hours poring over. And she found a lot of scruff in there. And most of it was just interference from terrestrial stuff. But not all of it. She found some that struck her as unusual. And with difficulty, she persuaded her supervisor to let her put special chart recorders that ran much faster on and turn them on when the scruff came by. One of the things she had noticed was that they came at almost the same time every day. Now, if it was the same time every day, maybe it's Mavis down the hill getting home from work and turning on her TV. But it's not the same time every day. It's 4 minutes earlier. And in fact, because of the way the Earth moves around the sun, stars rise 4 minutes earlier every day. And so this was the same place in the sky every day. And that sounded like something in space, not on Earth. So she investigated. And this is actually this is a scan of one of the chart recorder papers that she used. And this is the scruff. And you can kind of see there's a bunch of peaks, not all the same height, but they're all equally spaced. And that's strange. And they're spaced by about a second. And that's, you might see a planet spinning once a day, but once a second is crazy. That's way too fast. But it was perfectly regular. And so when it came time to publish, fortunately they found several, because one of their early theories was that this was aliens. And you can't publish a paper about aliens and be wrong and keep working in astronomy. Because, yes, but in their paper they didn't say anything about aliens, but they did name the source LGM1 and LGM2. Of course, that stood for little green man. I think they made up something else for it to stand for in the paper. But it turned out to be a thing called a pulsar. And pulsars are the cinders that are left behind when stars explode. So all the burning that can happen is gone. There's no fire, no heat left to support the thing against its own crushing gravity. And so they're tiny. They're the size of a city. They're a 10-kilometer radius. But they're massive. They're at least half again as massive as the sun. And so this is really hard to imagine how you could have such an object. It's incredibly dense and incredibly small. And it's also highly magnetized. It turns out if you take the magnetic field of the sun and you crush it down to 10 kilometers, it gets really strong. And if you take spinning, the sun spins about every 10 days, you crush it down to the size of this, like a ballerina bringing in her arms, it spins faster as well. And so these things spin rapidly and are highly magnetized. And it turns out that they produce beams of radio waves going out their magnetic poles. And you can imagine if this thing is rotating, the beam is going to sweep around the sky. And if you happen to be in the way when it sweeps past, you'll see a flash. It's like if you go outside and you see Pleasantville Marine spinning their searchlight around, annoying astronomers. If you were in line with the searchlight, you'd see it flash every time it went around. So we see a flash, although actually we detect a pulse of radio. We don't, it's hard to see these things in optical. But you see them in radio. And we study them here. I want to show you a nice picture of a pulsar. That was just an artist's illustration, obviously. But unfortunately, they're just point sources. They're 10 kilometers across. There's no way we're going to get a picture of a pulsar from here on Earth. So I can't give you a nice image of one. But they do pulse regularly. They vary with time. They get brighter. They get fainter. The pulses sometimes come early. The pulses sometimes come late. Sometimes the pulses are missing entirely. And that's interesting when that happens. So we study that. And so we use plots like this. This is something that I showed up in our group meeting today. But this doesn't look like anything to you, I know. And it's informative, but not interesting. So there are other ways to visualize what's going on with the pulsar. Since they're too small to see any detail, they produce radio pulses regularly. So you can sort of visualize them, I guess oralize them, by playing them out as sound. And so I'm going to play a few. So this is the crab pulsar. So it actually, the star that made it went off in 1054. It was actually observed to go off. I mean, suddenly there's a new star in the sky. People write that down. It was recorded in India, it was recorded in China, it was recorded in Japan, the Arabs recorded it. My own ancestors were busy grubbing in mud huts, Dark Ages in Europe, so we didn't notice it, but everybody else did. And so we know when this went off. We know how old it is. It's about 1,000 years old. And by astronomical standards, that's pretty young. This pulsar is still in its infancy. And so it's spinning about 30 times a second. Those of you with a musical ear might have been able to gauge that from listening to it. I can't. But that was about 30 times a second, which is, I mean, something the size of a city, that's pretty fast. But, and it's slowing down very gradually. And I don't have a picture here, but you can, it drives this wind of particles. You have a spectacular nebula, which you might, if you're lucky, be able to see. I think, again, probably not tonight. I don't think it's up. But you can actually see it with an amateur telescope if you look. It's an I forget what the number is.
M1.
What?
The crab is M1.
M1, okay. So M1. But unfortunately, I don't think it's visible tonight. But all that is powered by the pulsar. This is the Vela pulsar, which is older. It's 10,000 years old, so nobody wrote this down, but it's had longer to slow down. It's a little slower, so it spins about 10 times a second. And this is the loudest one in the sky. If you want to point a telescope at any old pulsar, this would be the one to point it at. But unfortunately, it's the southern hemisphere. But so this one is slower. It's older, it's slower, it's slowing down. This one is very old. Now, it's tempting to say that's really slow. You know, it's 1.4 times a second. That's pretty slow, right? Except this thing is the size of a city. Imagine pivoting Montreal around the cross on the mountain 1.4 times a second. So slow is a relative term. But this one is also slowing down. And you can measure it if you're determined enough. It's slowing down very gradually. And it's about 5 million years old. Now, this pulsar, this happens to be one that I study, is billions of years old. I say we think because it's a bit complicated, but it's billions of years old. It's much older than any of the others. And it's much, much faster. So if they start fast and slow down, how do you get one that's really old and really fast? Well, we think what happens is that you put them, is that if one of them is that you get a pulsar, it's born, it's fast, it slows down, slows down, slows down, we stop being able to see it, it just keeps slowing down gradually. But if it's got another star nearby, if it's orbiting another star, which this one is, and if that other star was dumping material onto it, gets so close that it kind of dumps material onto the surface, because the gravity of these things is very intense, they're so massive and so tiny. If you start dumping material on the surface, it swirls in. It doesn't just fall straight down, it swirls. And it's like, imagine having a ping pong ball floating in your bathtub. You pull out the plug, water starts swirling down, and the ping pong ball falls into a little vortex and starts spinning faster and faster. And so we think that's what happened to this guy, that it is spinning fast because it was spun up, it was recycled. It was an old pulsar that had stopped, or slowed down anyway, and was recycled back into a fast-spinning so-called millisecond pulsar. And this one, I studied it because it's interesting, because we think in 2001 it was actually still being recycled. So it might do it again sometime, and I sure hope so, but it's my thesis. Anyway, so there's a lot to study about pulsars. Unfortunately, they don't make great pictures, but you can sometimes hear what's going on with sounds. It's unfortunately, you can't measure things easily with sound, so this is more a visualization than an actual tool we use day to day. But to move on to other things. So our galaxy itself, this is actually a picture of the whole sky. There's actually a map of the hydrogen in the galaxy. Now, to an astronomer, the universe is made of basically three things: hydrogen, helium, and metals. Everything heavier than helium is just kind of a metal and kind of cumbersome. And the reason for that is that almost everything out there is hydrogen or helium. In fact, almost everything out there is hydrogen, full stop. And so if you map out the hydrogen, you map out what's in our galaxy, basically. And so this is mapping out the hydrogen in our galaxy. And it's using a trick, it's using the neon sign trick. Because hydrogen, when it's not too hot, emits radio waves at 21 centimeter wavelength. In fact, it emits radio waves at 21.1061141 centimeters. And that number comes from quantum mechanics and is universal. So if you see emission at 21 centimeters, that's probably coming from hydrogen. And you can map out how much hydrogen there is by seeing how much of that emission there is. What's more, if you see it at 21.2 centimeters, that means the wavelength is longer. That means it was moving away from you. The Doppler effect has lengthened the wavelength. So because you know what frequency it's coming from the hydrogen at, you can tell how fast the hydrogen is moving. So you can map out how fast the hydrogen is moving in the galaxy. You can map out the swirling of the galaxy. And the galaxy is full of hydrogen. So you can tell how our galaxy is swirling. After all, it's a spiral shape. And the stars are all going around, there's a lot of mass in it, so the stars want to fall in towards the center, so you have to be moving to keep from falling in. So you can measure how fast everything is moving. And so this is a graph of that. I mean, I don't expect you to read off the details. If it were like our solar system, it would look like this. The further out you get, the slower it gets. It's a little more complicated here because there's a lot of, not all the mass is at the center. It's not just the sun and some light stuff. There's stars all over the place. But you can measure how fast the hydrogen is moving, and so how fast the stars are moving, and how fast the galaxy is moving. And you can also measure, with other techniques, how much stuff there is in the galaxy, right? You can see the stars. The dust doesn't glow, but it absorbs stuff, so you can tell how much dust there is. You can measure all the other stuff that you can see. And you can figure out how much mass there is, and how fast things are moving, and whether they're moving fast enough to keep from falling in. And the fact is actually they're moving way too fast. They should be flying apart, but they're not. So there must be some mass in there or something is wrong. There must be some mass in there that we don't understand. And this is what we call dark matter, which you may have heard about if you read popular science things. And dark matter sounds more definite than it is. All we mean is there's something out there we can't see that has gravity. We know a few things about it. We know it's not clumpy like the stars, or it would behave more like the stars do. It's smooth. It's not distributed the same way the stars are. We know all galaxies seem to have it because you can do that trick on other galaxies too and see how they're swirling, even though they're far away. And they have the same problem. They're all swirling the wrong way for what you can see. In fact, if you add up how much of this stuff there must be, most of the matter that exists is dark matter, which is disturbing because we don't have any idea what it is. We've never detected it. We needed to make the books balance. In fact, recent studies show that there's another substance called dark energy that there's even more of, again, to make the books balance, even though we have no idea what it is. So there's plenty of questions out there still. And you can this particular graph, this one is a nice research grade graph, but you can actually, we have a small 2-meter telescope, radio telescope on the roof here, and you can do this with a 2-meter telescope. You can see the problem with that 2-meter telescope. Dark matter is we don't know what it is, but the mystery is within reach of undergraduate students here. You can actually do that experiment. So, but there are other things to ask about our galaxy. So you can look at the center of our galaxy, which which it turns out is in the Sagittarius, constellation of Sagittarius. And there's a lot of stuff there that pours out radio. This is a VLA image with 1 meter wavelength. And because it's the VLA, you can get a nice high-resolution image. And so you can see all sorts of stuff there. You can see this circle here is where a supernova went off, and there's one of those supernova remnants glowing. There's a couple more supernova remnants here. There's a lot of stuff at the center of our galaxy, and a lot of it is stars that went off. A bunch more supernova remnants. The mouse is actually one of these things that has a name because of it's a funny shape. It's there's actually a pulsar zipping along, and it's kind of leaving a wake of hot gas behind it, and the wake somehow looks a little bit like a mouse to the imaginative grad student who discovered it. So there's a bunch of stuff glowing around the galactic center. But right at the center, there's a hot glowing spot, and it seems to be just a single spot glowing really hot in radio. Unfortunately, you can't see this with an optical telescope because there's a lot of dust. There's stuff there, right? There's a lot of dust. And dust, it's like fog. You can't see through it. So you can't see the center of the galaxy from an optical telescope. But radio doesn't mind dust. So radio, you can tell what's going on in the center of the galaxy. And it sure looks like what's at the center of our galaxy. The thing right at the core of our galaxy is a gigantic black hole. Now, this is not totally unusual. Quasars, the quasars that Jocelyn Bell and Anthony Hewitt are trying to study, it turns out are actually black holes. That most, maybe all galaxies have black holes at their center. And we don't really know why, but it seems to be the case that they all have them, and that they're related to the way the galaxies form. Some of the black holes are actually gobbling up material from the galaxy. There's gas falling in, and a giant black hole is a lot of gravity. There's a lot of energy to be had from falling in. Some of the energy just disappears down the black hole, but a lot of it actually shows up as hot gas. It shows up as jets. Somehow, the material swirling in drives these streamers of material that shoot right out of the galaxy and into intergalactic space. These tremendous jets of hot plasma. And so these are called active galactic nuclei. Now we have a black hole in our galaxy. Fortunately, it's not doing that. But we don't really know why not. There's some stuff around it. I guess there's just not much stuff around it. It's kind of a mystery why ours isn't putting out this kind of crazy jets. But what I mean by crazy jets, this is the galaxy in Sept. We actually saw a quick shot of it in the other thing, earlier. But this, the black hole is a little tiny spot here. In fact, I don't know if you can see the box that this is zoomed in on because it's tiny. But this is the little tiny spot black hole that's producing all that energy. In fact, we can't even tell how small it is. But it's spewing out this jet that goes many thousand light years into intergalactic space. It has been doing that for years, millennia. So this, I wouldn't want one of those in the middle of our galaxy. It'd be kind of an uncomfortable neighbor. And it took the VLA, this kind of hot plasma, you can't really see it in the optical. You can't see these jets in the optical. These galaxies don't look like much of anything in the optical. Some of the jets you can see, but for the most part, you see them much better in radio. And so the VLA is a great tool. And the VLBA, the Earth-sized telescope, lets you zoom in on that and tell that whatever is driving it, it must be small. It must, 0.1 light years. Okay, that sounds like a lot, but to drive something the size of, that's as bright as the whole galaxy, that's amazingly focused energy. And it takes the VLBA to measure that that's really that small. Here's another one, 3C279. Again, sorry for the name. But so here you have the black hole at the center, and it's not smooth. It's not a smooth stream. There's a blob in it. And this is a series of images, from 1991 to about 1998. And this blob is being driven, it was fired off and is shooting out into the intergalactic medium at a tremendous clip. In fact, if you look at this horizontal scale, this is about 60 light years. And you might ask, how does it cross 60 light years in 8 years? It's actually an optical illusion. It's actually going further than 60 light years, but it's coming almost directly towards us. And because as it gets closer, we see it a little bit sooner. If it's 2 light years closer to us, we see it 2 light years sooner. We see it 2 years sooner. So that compresses the time scale. So it looks faster than it is. So it's only almost the speed of light, not faster than the speed of light. But this is still, I mean, you've got this black hole center together that fired off this tremendous blob of gas that we can see from millions of light years away. And it's firing this, I mean, this is happening all the time. This isn't destroying the galaxy. This is just a steady process of firing out these blobs. And it takes, this is again a VLBA observation where we can actually measure the motion of this blob of gas over the span of 8 years. And it's very rare that we can see something change this quickly that's that huge. One final sort of amusing thing we do with quasars is if you want to measure how the Earth is rotating, you want to get very precise measurements of the Earth's orientation, you need signposts. And stars kind of fly around in the galaxy. But quasars are so far away they can't move. So we use quasars actually as signposts to measure the Earth's rotation. And this is how people decide whether we need a leap second this year. I don't know if you have come across leap seconds, but every so often we add an extra second to keep noon at exactly noon. And finally, the Big Bang, the cosmic microwave background. It was actually discovered by radio astronomers who were trying to figure out what that noise was in their satellite observations. And it turns out that noise was the Big Bang. The Big Bang is so far away and it's moving away from us so quickly, so redshifted, that it's cooled to about 3 kelvins, to about 3 degrees above absolute zero. But it turns out you can observe that really well with a radio telescope. And I agree, this one's kind of goofy looking, but it was effective. These days we use better telescopes that aren't really radio telescopes. And we can map out tiny variations in the Big Bang. And this is irregularities in the Big Bang itself. And some of my colleagues here can tell you way more about this stuff, so I won't get into this. But you can, it was radio astronomers who first noticed this radiation left over from the Big Bang. I can talk a little bit about the future of radio astronomy. I'm just going to show you some pictures of telescopes to come. LOFAR is taking the idea of an interferometer one step further. For one thing, there are stations, this is the Netherlands, stations as far as Germany and England. And if many smaller dishes work well, how about lots and lots of things that aren't even dishes? They just have arrays of little dipole antennas, no reflectors, no moving parts at all. It's all done by clever electronics and clever digital synthesis. And this is a low frequency antenna that can actually, it's already running, it's coming online now, and it's extremely sensitive. It's a terrific antenna. The Chinese are taking the Arecibo idea one step further. This is 500 meters in diameter. They're building basically a giant Arecibo. Slightly different design, but same idea, giant dish over a karst valley. And finally, the big radio astronomers' holy grail is a square kilometer array. Now this is not an array that covers a square kilometer. I mean, that would be big, but not that impressive. The idea is that the total area of all the dishes adds up to a square kilometer. It's like taking a kilometer by a kilometer and just paving it entirely with dishes. And you spread them out over many, many miles of Australian desert or South African desert, depending on how they decide. And this will be a tremendous boon to radio astronomy, but it will also take a long time to build, unfortunately. I have to get my thesis before it's done. Anyway, so there's a lot to do with radio astronomy, a lot of new telescopes coming online, but I think it's an exciting field where you can see cool things. But I think it's now about time that you guys go see cool things with your own eyes. But just quickly, are there any questions? Yeah.
Isn't there another array that's being built in Chile?
Oh yeah. Well, yes. So that's called ALMA, the Atacama Large Millimeter Array, and it specializes in the very shortest wavelengths that you can do radio astronomy with. And it's also coming online, and it's going to do fabulous work. But it's sort of higher frequencies than I'm used to working with. I'm used to like 20 centimeters, and it's going to be like millimeter wavelengths. Yeah.
Is there any limit to how good, long or short electromagnetic waves can be?
Essentially, no. But there are limits to what we can see on Earth, because the atmosphere bounces things longer than about 10 meters, and it bounces things shorter than about a millimeter. ALMA is kind of pushing the limits of what you can see through the atmosphere. There's actually, if you put a radio telescope in space, it can go further down. You don't need to worry about being bounced off the atmosphere. But there's a limit to the frequencies that can propagate through the interstellar space. So there is a lower limit to what you can observe with radio astronomy. What we haven't explored down there because it takes satellites to do it. Yeah.
What are the advantages of Arecibo over the VLA?
So the VLA has high resolution, but it can only collect as much radio as hits its dishes. And 27, 25-meter dishes is roughly equivalent to 100-meter dish. Arecibo has 300-meter diameter. It collects 9 times as much signal. And that's a tremendous advantage because we're always looking at the faintest things we can see. So the bigger your dish, the more radio you can collect, the more valuable it is. There are also other advantages when it comes to the complexities of processing the VLA data. If you're looking at something that's really just a point source anyway, it's way simpler to work with Arecibo data. You can do, because it's simpler, you can do more things. So there are advantages to both. Yeah?
You were saying that hydrogen pulsates at about 20.1.
21 centimeters, yeah.
So when you see it pulsing at, say, 20.2, you know that it's moving away because it's the Doppler effect. How do you know you're not looking at something else that naturally pulses at 20.2?
It's a good question, but there's actually a very limited number of, I mean, this is, you get the answer from quantum mechanics, 21 point whatever quantum mechanics. And there just aren't that many things that it could be. More complex molecules, the frequencies are higher up. And so when you're dealing with more complex molecules, and I mean, this is how people have detected like sugars in space. You look at the particular frequencies they emit, and those frequencies can be confused with other things. So the more complex molecules, it's tricky. But down at the hydrogen frequencies, there's not much to confuse it with.